Today we are fortunate to have Professor George Wolberg from CUNY in New York to talk to us. You may know him for his work on warping. He has a book that is fairly famous about this called Digital Image Warping. That led him to, he had a Presidential Young Investigator Award in '91, and in 2000 he even got the Mayor's Award for Excellence in Science and Technology from Rudy Giuliani. And today he's going to talk to us about new algorithms for mapping 2D imagery onto 3D models and range data. So,
thank you. I'd like to thank Luke for inviting me today to talk about multiview geometry for texture mapping 2D images onto 3D range data. The motivation of this work is to develop 3D photography software. And by that I mean the ability to import the geometry of large-scale urban environments. So it's very easy, of course, to bring in images into the computer with a digital camera, but how easy is it to bring in geometry? And so that's the problem that we're facing. And we're trying to distinguish our work by having models of high geometric and photometric accuracy. And so the thrust of this talk will be about how to do automated texture mapping for photorealism. So we'd like to position our software as basically an Adobe Photoshop of 3D photography, if you will. And by that I mean a comprehensive software toolkit to be able to do the modeling and do the texture mapping as automated as possible. Okay, so we have two sources of inputs for our work: range scans and ordinary photographs. Now, as far as the range scanning goes, we are currently using a Leica 2500 spot laser scanner. It's of the time of flight flavor. Okay, laser scanners can come of time of flight or phase-based. And we use time of flight because that allows us to hit a maximum range of 100 meters. So for large-scale structures like buildings, we need to be able to image it from further away. This particular one happens to be a little slow. It's about 16 minutes for 1 million points. Phase-based scanners are always much faster, but they are less accurate, and they can only reach a distance of about 25 meters, 25 to 50 meters. So, whereas time of flight can go 100 meters, even a kilometer away if you want, if you're willing to tolerate a little bit more error. The error we get here is about 6 millimeters per range point. So as an example of 3D photography, let's take a look at the image on the upper left. That's a photograph of the Thomas Hunter building in New York City. And on the lower left, we see an example of several range scans that were seamlessly tied together. Okay, so this is done without human interaction. Every range scan is shown with a different color. So we have to take multiple range scans because, of course, we have to get at all the sides of the building. And the key here is that the registration is done automatically. Here's another example. This is the view outside my office. This is Upper West Side Manhattan. This is the Shepard Hall building on the campus of City College. In fact, if you look closely, you could see Yankee Stadium in the distance right there. Here we took 24 range scans around the building, and what you're seeing here is just a point cloud of the 24 range scans all stitched seamlessly together. So we didn't do any meshing work. We just collected the points and displayed them as a point cloud. Of course, if you go very close to the point cloud, you will see gaps. And there are different rendering ways, like QSplat, if you want to render point clouds. Or you can just directly mesh this. OK, so here's an example of where we're trying to go with this. You see that building that's modeled as a collection of point clouds. And you'll notice these white spheres. They represent the automatically recovered positions of the cameras that we took to take photographs of this. So you remember I said that there were two sources of input, range scans and photographs. So in order to get the proper color and texture for all this, we have to walk around the building collecting photographs, and our method automatically can recover the positions of the cameras. And each one of these white spheres is connected to a green sphere, which shows you the optical axis of the camera. So it shows you not only where we were standing when we took the pictures, but also how we were holding the camera, which orientation. So that's all part of the software toolkit that I'll describe today. Okay, so the applications of this work is to come up with photo-textured models for Google Maps and other similar products. So for instance, right now you have SketchUp, as a method for creating lightweight, low-resolution models that you can put on satellite maps. The question is, how would you get higher detailed models? It's not going to be done through SketchUp. It will be done through the use of laser range scanning and also photographs that can apply photo textures to it easily. And the key point here is not can it be done, but can it be done automatically? Okay, because obviously if you put enough manpower behind any problem, you will solve it. But the question is, will it be solved efficiently? And will it scale up well? And this is the work we're trying to do, to make it scale up. So another application of this work is 3D auto navigation systems, the next generation of navigation systems for cars. And that ties in with video games, because sometimes that looks like a video game when you drive through a city and you're trying to make a digital city out of this. So realistic sets for movies and video games, urban or military planning, virtual tourism, modeling theaters and stadiums so that you can get virtually assisted seating selection. You could see what your seat would look like if you were to buy this ticket at this location. Okay, so we will address several problems here. First problem is feature-based texture mapping. Now currently that requires extensive human interaction for feature selection among 2D images and 3D range scans. Another problem we have to address is what happens if there's a rigid attachment of a camera onto the scanner. There are many laser range scanners that are sold that have cameras built in, but unfortunately that constrains the time and the place of image acquisition. In the example of scanning buildings, it may take several hours, maybe the large part of a day, to scan a very large building. And we don't want to use the photographs that are acquired from that laser range scanner because they will vary in shading from sunrise to sunset. So we would like to be able to have a model on the one hand and photography that could be mapped to it, taken at different times of the day. So you could show what that building would look like at sunrise or what it would look like at noon or near sunset. Okay, so that's another problem we have to address. And also the seamless fusion of geometry and photography, which currently requires manual interaction. So the solution that we're proposing is to integrate multiview geometry and 2D to 3D registration in order to texture map onto 3D range data. So as I said before, we will have two sources of input for this problem. The first one is dense 3D point clouds that are derived from laser range scanners. And the second source of input are just ordinary 2D photographs taken from arbitrary views by off-the-shelf cameras. So the outline of this work is to produce sparse point clouds from photos by multiview geometry. Okay, so on the one hand, we'll get a sparse model, a low-res model. Then we will project the 3D points from the dense point cloud that we obtained from the laser range scanner. And from the sparse point cloud that we obtained from the camera, we will project those 3D points together into a common image. Which image? The images that we took as we walked around the building. Okay, and then common 2D points between them will establish correspondence among the point clouds. And we will therefore recover the rotation, scale, and translation to best align the dense and the sparse point clouds together. And the purpose of doing that will be to bring all the photos that we took around the building into a reference frame of the dense model so that we can do texture mapping. Now that's a lot of high-level outline. It's probably best described with this slide. So if you didn't understand what I just said, hopefully this slide will clarify it. On the top part of the slide, you see a collection of 22 images that we took around the building. Now, we took those images and we go down the right branch that you see here where it says structure for motion. We use those images to create a sparse point cloud just from those images alone. And alongside with that sparse point cloud, we can also recover the positions of the cameras that took those pictures. Okay, so that is one branch of this work. The second branch is using laser range scanners on the left side, and then using these images to figure out where do they lie with respect to those dense point clouds derived from the lasers. And as you could see here, you see 5 white dots. And they represent only 5 images, namely the ones that are outlined in blue. And only those 5 images out of the 22 were able to successfully be mapped to that dense point cloud. In other words, only those 5 images, we were able to figure out where we were standing when we took them. But that leaves the other 17 images to basically provide us with no useful information there, which is a waste. So what we would like to do is merge the benefits of this branch, which has a dense point cloud and only 5 photographs that can be projected to it, and this branch, which produced a sparse model but has all 22 positions that are identified with it, bring them together. And if we bring them together, that means we will have the benefit of projecting the color information from 22 photographs onto the model, rather than just from 5 photographs. And we're trying to do this automatically, okay? There's no manual intervention here. So this line of work, the structure for motion, is pretty well known in the computer vision field, okay? It stems from original work dating over 10 years ago by Faugerat and his colleagues at INRIA. And the work on the left branch was presented last year by Yannis Damas and his student Lingyun Liu, who is actually a summer intern here this year. And that was presented last summer at a CVPR conference, 2005. So what I'll talk about today is the contribution of this work of bringing the two together, merging the benefits of structure for motion and 2D image to 3D range registration, so that you can come up with the results shown in the lower right, which is a nice photo-textured, accurate model of the building. Okay, so if you look at the left branch, the 2D image to 3D range registration, we can describe that using this slide. There are, again, 2 sources of input, range images and 2D images. In the case of range images, what we will do is undergo a process of 3D feature extraction, which is shown in this box on the left. The 3D feature extraction consists of 4 steps: 3D lines extraction, followed by range registration, followed by 3D line clustering, and 3D cube extraction. The purpose here is to be able to match up or to be able to extract the 3D lines that are present in the range scans. Now, we're fortunate when we look at buildings that there are a lot of linear features in buildings. In all of these man-made structures, they are linear features. So we will exploit that information. We will extract it from the range scans, and we will figure out what are the rectangular parallelepipeds, or what are the cubes that we could extract from the point cloud. Now, alongside that, we will look at the 2D images and see what are the rectangles we can recover from there. So we obviously can recover 2D lines, linear features, off of the photographs. We can use that to recover vanishing points. And we can use that to help calibrate the camera and rectify the lines that we just extracted, so that we can come up with 2D rectangles. Now, these 2D rectangles might consist of the windows in the building or other features that are prevalent in the building. So we are going to do the matching between the 2D features in the photographs with the 3D features in the range scans, so that we can figure out how to best match the photographs to the range scans. In essence, how to do this texture mapping automatically without having to go in by hand and say that this point in this image corresponds to that point in the range scan, which is the current state of the art. So just to look at 3D feature extraction in a little bit more detail, on the upper left you see an example of range scans. And in the second row there, you see 3D lines that are extracted from those range scans. And then we use those lines to be able to connect one range scan to the next. In other words, to align these multiple range scans together and register them, which is shown on the bottom left. Then we can cluster lines so that we can find that these lines lie among 3 major directions, the X, Y, and Z axes. And we can use that 3D face extraction and then extract rectangular parallelepipeds from the building. Okay, so we are using the man-made features that are prevalent in the buildings and using them to extract rectangular parallelepipeds, or small cubes, if you will. And then alongside that, we do the same thing for the 2D images. So we do 2D feature extraction. And we take photographs like you see in the upper left. We extract lines off of the photographs. And we use those lines to figure out vanishing points. And then those vanishing points are useful for us to calibrate the camera and to rectify those edges so that we can have a rectified edge map, a rectified set of 2D lines. And then we can extract rectangles off of that. So then we will map the rectangles off of the photographs from the rectangular parallel pipeds off of the range scans, and we will be able to bring these two different domains in sync. So, here we see that slide again, and we just, briefly overviewed the 2D image to 3D range registration, which is that left branch over there. What we need to do now is then go over how do we get this right branch? How do we derive the structure and the camera positions directly from the photographs alone? In order to do that, we use what's called Multiview Geometry, and it goes by several other names, like Structure for Motion, and SLAM, which is Simultaneous Localization and Mapping. So if you look at some of the computer vision literature, you'll find these 3 different names, but they're all the same thing. The idea here is to recover the camera positions from the images, to bring one camera into the range scan coordinate system, and then all the other cameras will follow as a rigid transformation. But in case there are some errors, we use bundle adjustment to best distribute the errors across all of those camera positions. And what we get out of this is that it facilitates automatic texture mapping from the photos taken at arbitrary positions. And that's key. We don't want to limit anyone, where they can take pictures from. And we can use just regular off-the-shelf cameras to do this. So here's the kind of high-level overview of how this is done. Okay, we start with frame 0 on the left, and we use SIFT, which is a scale invariant feature transform, to derive features off of that image. Okay, and these features are such that they are scale invariant. So we can assume that there is a transformation associated with that frame, namely K times I, the identity matrix, and 0 for translation. So in the square brackets, basically it's composite or partitioning of the rotation matrix and the translation vector. Initially, we will assume no rotation, no translation. So that's for frame 0. Everything will be anchored around that. K is a matrix that stores the intrinsic parameters of the camera. So we will find these black dots here, which represent the SIFT features. And then we have to do that for all images. And we can use correlation to basically see where this feature lies in the next frame. Where does this feature lie in the next frame? We do that for all of these features. Now, because we know the essential matrix, we can recover the initial R1 and T1, the initial rotation and translation that best takes the camera from frame 0 to frame 1. So we will use essential matrix to determine R1 and T1. And that means that when we know this point maps to this point, we can use that information to triangulate and find out where does it lie in 3D. Because we will have recovered the initial rotation and translation using essential matrix. So the initial pair can be resolved that way, and we can basically get a very small point cloud out of that. So if we have, let's say, 10 features that are found in frame 0 and frame 1, that means that they will correspond to 10 points in my point cloud. But then I have to propagate that information to frame 2. So I also do correlation. For instance, this point that was found, connected to this point here in frame 0 and frame 1, that point can also be connected to frame 2. So I look at this pair, and I look at the other pairs that have connections. And for all other frames, we have to compute the unknown rotation and translation using a 6-point RANSAC algorithm. That's random sampling consensus. And the purpose of that is to help eliminate outliers, because you may have some errors, so you want to make sure you don't consider outlying solutions. So that basically helps you, because that means that the 3D point that was connected, or that was due to this connection here, that 3D point is also shared to that feature point here. And so what we are doing is progressively adding more and more points to our point cloud. So as we consider, from 2 to 3 to 300 frames, we are building up the point cloud with contributions throughout. So this is how structure for motion works, which means that if we are taking pictures of things that don't have features, like let's say this wall right here, which is a plain wall, there's very little features to track onto, structure for motion will not work. It only works when there are features to grab onto. Okay? So in the example that we had with that church-like building, the neo-Gothic building, it's a stone building, and there were many features to grab onto because there's many interesting visual points on that stone building. So then we have to apply global bundle adjustment to distribute the error of the camera pose and structure. Because otherwise we accrue error as we go along. And we want to distribute the error uniformly. So what we do is we minimize the summation, which tries to minimize the distance between little m, which is an extracted 2D feature point, and capital P, capital M, where P is a projection matrix, and capital M is a 3D point. So in other words, the projection of a 3D point should land very close to its corresponding position in the image, little m. And we try to minimize that distance by varying by varying m, capital M I should say, and by varying P. So we will basically minimize this reprojection error. And we can solve this efficiently using a technique called sparse bundle adjustment. So as an example, here is what we get. Let's say we are walking, with the 22 photographs that I took before. Remember, we don't have GPS on this. We can't trust it. In urban canyons, you're not going to get good results with GPS anyway. So what we do is we walk around the building. And as we walk around the building, we take these pictures. Remember, we don't know where we took them from, but that's the whole point of this exercise. Structure for motion is supposed to give you that information. And that information is displayed here as those little white dots. Okay, so those little white dots is some of the results we get from structure for motion. Where did we take those pictures from? And simultaneously, along with that, we also get the sparse points that you could almost make out that building there, right? From the sparse point cloud. And those two come together simultaneously because you need, you're basically balancing both, the 3D position and the position of the camera. So you are getting the sparse point cloud, you are getting the recovered camera positions. Okay? Now, if we were only to project the photograph from, let's say, that last photo, which is shown here, onto this structure, then you might get something. Oh, wait, hold on a second. Let me back up a second. Okay. Let me just go here. Okay. I'm not gonna show you that part here. Well, if we were to project this photograph onto this point cloud, you will only get a subset of the pixels rendered. And then as you add more and more of the photographs onto the point cloud, you will get the more richly painted structure. But what I'm showing you here, or what we've just reviewed, is how to go down this branch. How do we go from these images to this sparse point cloud for which we know all the camera positions? Now the next step is to bring the two together. The next step is to say, I've got my sparse point cloud, I've got my dense point cloud from the lasers. How do you merge them? Okay, so what we do is we figure out how to merge it. And notice what's happening. We take our little sparse point cloud, for which we didn't have the right scale, and we bring it into the right scale of the dense. Because remember that all of that work with structure for motion was scale independent. No one said that the size of this brick is, however many inches. Okay, it's all modulo scale. So we have to bring this into the same scale and reference frame as the dense. And that's the next part here, which is to align the range scans and to align the sparse structure for motion point clouds together. So how do we do that? Okay, what we do is we take those images. Remember we had 5 images for which we did find correspondence between the image and the dense point cloud. We take one of those 5 images, let's say this one here, and we consider what happens if we project the 3D point from the structure for motion onto that image, and also project the 3D range point onto that image. So we're looking at a little subset of this image here, and in this image that you see on the lower left, you see what happens when we project a point from the sparse point cloud onto that image. You get a collection of those colored dots there. Now look what happens on the lower right. You also project the dense point cloud onto that very same image. And you get this collection of dots. Now for every dot that you see here projected on the lower left, what we do is we look for a close position here on the other image. So what we do is we basically consider a candidate, that this point here has a candidate match in this vicinity here. So 2 points are a candidate match if their 2D projections in this image are near each other. Okay, so what we're trying to do is figure out who is a match to whom. And we can do so if if a match is considered compatible if their scale factors are approximately equal. So going back to this slide, if this 3D point that gave rise to this 2D projection is closely associated with that one, then that means that the 3D points from which they came should be the same. They should be corresponding. But how do we know that that's true? So what we do is we go through this set of procedures to find that. And we're exploiting the fact that scale factors should be the same between both of those point clouds. Remember that when we recovered the structure from motion point cloud, we didn't know its proper scale. But we can try to find out what is the best scale factor to bring it up to the other point cloud. So we consider a point from the structure from motion point cloud minus the center of projection, which is the camera position, and divide that by the corresponding point that we're considering from the range image minus its center of projection. That will give us a value S1. Then we do the same thing on another point, on some other point that landed in these two images. That will give us S2. And then we take the difference between X2 and X1 from the structure from motion, divided by the difference between some other candidate, Y2 and Y1 from the range. And the idea here is that the confidence of a match is based on how many compatible matches you have in terms of scale. Okay? So it's almost like a voting scheme, where a lot of the points will vote, and you will see that they converge on one optimal scale factor, S sub opt. And if we assume that that is our correct scale, then we can come up with a list C of robust matches such that the match between the corresponding point in the structure from motion in the sparse model and the point in the range model satisfy that scale difference. And they satisfy it for all the points. Okay, so once we recover, we go through all this effort just to recover an optimal scale value S. So once we recover S, then we can go ahead and minimize this equation that says, what is my unknown rotation and translation that best brings these two point clouds together? So we went through all this effort just to figure out what is the proper scale to take that sparse model to the dense model. And once we figured out that scale, then we solve for the remaining two parameters, which is rotation and translation. So if we go back to that video that you saw here, let me see if we can get that to work. Right, if we go back to that video, this makes it almost look like it's incremental, but it's not. The idea here is that we found the right scale to go from the initial configuration to the final configuration. And if we're in the right scale, then all of these camera positions were carried along with it, including the, and they match up with the 5 that we recovered using the old method based only on the dense laser scan point cloud. So the idea is that we carry over the known camera positions that we knew from structure from motion, and we bring it into the same reference frame as the dense point cloud data that we got from laser range scans. And this is what enables us to do the texture mapping automatically. The fact that we were able to know where the camera positions were and bring those photographs into the same reference frame. And it's not done manually. You don't have to say, oh, this point corresponds to that point, the good old-fashioned way. But it's done automatically through this process. Okay, so compare what we had before with the dense 3D point cloud and only 5 recovered camera positions. And then compare that with what we have now, which is a whole set of additional camera positions that we were able to bring along. And that just serves to make this a more richly textured model. It's better to use 22 photographs rather than just 5. So if we look at the results, let's say from only that viewpoint. Imagine that we had the camera here, we took a picture from this viewpoint and projected onto the point cloud. This is what you would get. You would only get part of the building that is properly textured. The rest is unknown. But as you consider more and more cameras and you project or splash those colors onto the model, then you get everything else. Okay? So that's how you begin to color everything, because you are using a greater number of photographs. In other words, you're using all 22 that you had available for you, rather than just the 5 that we were able to figure out from the 2D to 3D registration solution. So this is a big step forward. Okay, and as you could see here, these spheres represent the recovered camera positions, and these lines represent the angles at which the cameras were oriented. And this is what we were able to get. If we're missing some other parts of the building, it's because we didn't have a viewpoint from which to take it from. Normally, we would like to be on a tall building across the street from it so we could look down or perhaps get it from aerial imagery, which we did not have available to us. So here's the animation again. So this is just a synthetic rendering of the building. It is animated here. Again, you can see the overlay camera positions that we automatically recovered and the orientations. And you could take photographs at many different times of the day and then create different animations with lighting at different times of the day. So that's the benefit of decoupling the camera part, the photography, with the model generation using laser range data. Okay, so this example of Shepard Hall used about 12 million 3D points derived from the lasers. In this example, we will look at this column here. We used 22 images from which we generated 45,000 sparse points in the point cloud. So when I talked about the sparse structure for motion 3D point cloud, it was sparse because it only had 45,000 points instead of 12 million. So 12 million is what we got from the laser, 45,000 is what we got from the photographs alone. And if we were to use the 2D to 3D registration alone, we would have only known 5 camera positions. Instead, we now have the benefit of using all 22 when we project those images onto the building. And this whole process took about 19 seconds. Okay? And this is on some standard Dell computer, about 3 gigahertz, nothing fancy. We also did this work for National Geographic. And this work aired in December. They did a documentary on the history of Grand Central Terminal in New York City, which is a very large structure. And so we went in there on 2 nights. The only times we can go there when there were no people, between 2 and 5 a.m. And at least we were able to get that time, because if we were at Penn Station, it's always open. There's no such access. Okay, so we were able to collect about 44 million points through laser range scans. We used 2 scanners. We used the time of flight scanner, especially for the ceiling part, which is very far away. And we used also a phase-based scanner for some narrower passageways that were closer to us. Okay, so here's an example where we took just a few images here, projected them onto the 3D laser data, and you get something that's photorealistic. And that was the purpose of this work, so that you could basically have something photorealistic enough you could fly through in physically unrealizable ways with a camera in Grand Central Terminal. Okay, and this work is currently under consideration for an Emmy Award. I guess we'll find out in 3 weeks if we got it, or if we were nominated or not. Okay, so that's the work for Grand Central. So let me wrap this up. What I spoke about today was the integration of multiview geometry with range registration. We use 2D to 3D registration for a subset of images that contain a sufficient number of linear features. And the purpose here is to bring these images into alignment with the dense 3D range model that we acquire from laser scanners. The concept of bringing in multiview geometry exploits the 2D point correspondences. They allow us to bring all images into alignment and produce the sparse SFM model. And then we go ahead and we align all the images with the dense 3D model. So as a result of this work, we can have accurate texture mapping onto dense 3D range data. Okay. So I'd be happy to entertain any questions you may have. Yes?
When you scaled the structure for motion camera 3D point data to the range data, it appeared that you started immediately with the point cloud. And when you brought those 2 images into scale with each other, obviously the camera is lined up as well. Wouldn't it be a good optimization to try to align the cameras first, at least to get really radically close to the final solution, and then apply a point cloud match?
Okay, let me repeat the question. In the case, let me go to the slide that's relevant here first. Let me see here. Okay, let's say this slide here, right?
Yeah.
Okay, so the question is, related to this problem of scaling the SFM model and aligning it best to the dense model. We use the points directly to determine that. You're suggesting that perhaps we could have done this directly from the camera positions here.
Because you have 5, right?
Right.
And it seems like it would be easier to try to match that 5 in your set of 19.
So 5 to 22, yeah. So we could have matched the 5 to the 22.
Oh, they already matched.
What's that?
This 5 already matched. It's a subset of the 22.
Right, so what I'm saying is you could use that to then get a close scale, right?
Right, so the point is, why not just directly map the 5 here to the 22 rather than project these points into an image and project these points into an image and then work off of that scale information?
Well, yeah, as a starting point.
Right, as a starting point. I suppose that could be used as a starting point. The problem here is that how do you vouch for the accuracy of these 5 and these 22? By using the abundance of points that we recovered from the point clouds, that would help us minimize the error. Okay, so it's more for error minimization. But I suppose that would have been a good initial guess. Yes, you have a point.
And also, we can use only one image. We don't have to use 5. So sometimes we don't get enough to the image to correctly register with the range data.
So if you're lucky, you get 5. If you're not lucky, you get 1.
Yeah, if we have more, we can use this to get a good image of. If we don't have such enough,
Okay, so another point that was raised is that, in this case we got 5, but that's a function of what images you are collecting. You might get 5, you might get 1, you might get 2. So, if you only had 1, obviously you couldn't really do that. So you need at least 2. But, it could serve as an initial estimate. It could. So that point is well taken. Yeah. Yes?
So you map the sparse data points onto the dense data points, but do you then throw them away? Or, for example, if you have an aerial plane taking a photo, you can't very well stick a laser range scanner on your plane that's flying, doing a fly-through.
Right.
So you get data from just the 2D images, and you can recover some sparse data from that would not be in your dense data. So do you use that for, like, say, roofs?
Okay, so the question relates to, well, if we were flying over with a plane overhead, we would only get the imagery. We would not get range data from that because we're not going to get this type of accurate laser range data. You could fly LiDAR, but then it's very inaccurate. Like there are some overhead LiDARs that you could use, but they're not really worthwhile for this purpose. For that application, we could get another source of 3D points from the air by using what's called push broom mosaics. So an interesting area of future work would be to just use imagery to get a reasonable estimate of the 3D data by using what's called push broom mosaics. So by that means that you have an image and you consider one scan line, actually you consider 2 scan lines, one that's forward looking, one that's backward looking, and you think of them as slits. And as you move from frame to frame, you are creating a mosaic for which you do know the baseline distance between those 2 slits. So you can derive what in effect is stereo imagery, which gives you 3D information by just flying overhead. And then you can use that as your estimate for depth instead of the laser scanning results.
But already you're getting some data points using structure from motion.
Right.
So do you use those at all? Do you add those into your dense graph?
Okay, so the question is, do we add in the 3D data points that we got from the sparse point cloud in addition to the dense? And the answer is no, we don't need to. We don't.
But it seems like those would give you some additional points that you're...
They will give us additional points, but they're not as accurate as the dense ones, as the laser ones.
But something's better than nothing.
Something's better than nothing, but would it be good enough, let's say, to do this whole exercise without any laser points? In other words, can we just go down this right branch and be satisfied to get a result like that in the lower right? And, often case, it's not enough. It gets you part of the way there.
I'm not saying get rid of the 3D data. It just seems that the 3D dense data is missing some areas that you can augment with lower quality.
Actually, that's not. You're saying that the 3D dense data is missing that we could augment with lower quality sparse, but that's not really the case. The dense is so much down. 12 million points compared to 45,000.
Yes, but if you have a plane flying over, you get images of the roof which you can use the structure from motion to go from the side over
Okay.
to the roof that the laser
Right.
wouldn't be able to do.
Right, okay, so let me repeat that point. You're right, that overhead, when you fly overhead, you will get roof data, the 45,000 or whatever it is, that will be better than the no data that you would have acquired from the ground using lasers. And then we can pull those two together, and that's correct. We haven't had that access to that aerial data yet, so if you have access to it and would like to share it with us, we'd be glad to do that. Yes?
How would you handle the faces of the building that you don't have access to? The roof, the bed?
Right, we have, okay, the question is how do you deal with faces of the buildings for which we do not have access to, and the problem is we can't right now. We have to go ahead and possibly edit it by hand, so that's where maybe SketchUp would be helpful to augment all of this work, and sketch up the rest, so that you can kind of fill in the gaps. There's nothing we can do for parts that we don't know. I mean, unless we can do model fitting, unless you think that this part of the building has like a triangular rooftop or some other, then you could try to fit models, and that's almost like a Canoma-like, application where you can kind of fit primitives to existing structures, and that might be an interesting application. But right now we can't do anything with these holes if we can't gain access to it. Yes.
In the 2D to 3D range registration, what is it that limits the number of images that you can actually register? Why do you get the 5 instead of the whole set?
Okay, so the question is, what limits us, let's say, to get 5 such points instead of more? Well, what is the problem here? Lingy, did you have a comment you wanted to say about that?
Can you repeat the question? I'm sorry.
Well, in the 2D to 3D range registration, you're only getting 5 images registered. So presumably you've tried all of them.
Yeah.
So why are you only getting that 5? What's the problem with the other images?
Oh, the problem is that other images doesn't support enough linear features for the 2D to 3D registration. So they can register the image with the 3D range model, but in the wrong way. So we cannot use them for texture mapping.
So there's simply not enough common features.
Right, so let me summarize. There aren't enough common features necessary to match up the 2D images with the 3D range scans on all those pairs, except for the 5 that are shown there. And it's just a scene-dependent problem. Depends on where you were standing when you took these images, where you were standing when you took these laser range scans. Do you have these features in common? And the whole purpose here is to decouple the act of photographing the building from the act of scanning it with a laser scanner. And in doing so, you run the risk that you may not have good enough vantage points from both to match them up. So it probably would have helped if you record the positions from which you took those laser scans, and then pretty much come later with the camera and stand on that same spot. That would be greatly simplifying the problem. We didn't do that. We allowed you to freely, arbitrarily walk around the building taking whatever pictures you want. Yeah.
It seems like normally when you try to texture map, say, a model of a building from images, the fact that trees include the building is kind of a deal killer. I was wondering if you're doing something special to handle that, or if there's something about your example that makes that problem go away. Okay,
so the question is, how do we deal with outliers of trees and things that we're taking pictures of the building, but these trees and cars or whatever get in the way? The way we resolve that is the fact that we're taking so many images that from some vantage point, you will avoid seeing the tree. So it's just, the greater the abundance of imagery you take, the easier this outlier removal becomes.
Can that be automatic then, or is that something you have to kind of look out for?
Can it be automatic? Well, you can automatically figure out some of the depth positions of these outliers, and then you can, if you want, just establish clipping planes, to just cut it out. I'm not saying that it would be automatic. I mean, somewhere you have to establish that this is meant to be on the building or not. I suppose it could be if you just follow the contour of the facade and then you cut out everything outside of that. Yeah, you could try to automate that. Yes.
I understand the laser is infrared. So do you get different signals because the camera is in one spectrum and the laser is infrared, so you get different data?
The question is, do we get different signals because the laser range scanner and the camera operate in different parts of the spectrum, infrared or not infrared? And we haven't noticed any problems with that. Generally, the edges line up. When you have a corner in the building or some other facet, the edge that the laser scanner finds is in sync with the edge where the photograph is. So we haven't hit any problems with that. Although you're right, there could be some slight displacement, but besides, at this level of texture mapping, you would never see that. Texture mapping was originally introduced to cover up artifacts with low geometry, with something that's not richly modeled, and so that type of effect would not be even visually perceptible. Any other questions? Okay, so I'll be around for a little while afterwards. I'll be happy to entertain any further questions you may have. Thank you very much.